Hi, this is going to be a quick review of the things that are in Chapter 7 notes. I thought I'd go over it this way with you to try to make sure we're staying on track and getting some of the things that we have to cover, even though I'm not there. So let's take a look through. We'll do this in segments, and they'll be short. So the first thing I wanted to go over with you in Chapter 7, Chemical Bonding Unit. So this whole chapter deals with ionic bonds. So we already talked about what's in page 1 and 2. We talked about how you can use electronegativities to predict what type of bond you would have, ionic, polar, or nonpolar covalent. So what I'd like you to do right now is just move forward to the naming of the compounds. All right, so that'll be page 8. So go to this page, Formulas for Binary Ionic Compounds. So this would be like one of the goals. So goal for this one, for this section, you should be able to write an ionic formula given its name. So we're only going to do this part of it right here. So an ionic formula is, first off, you have to realize, most important, we'll highlight, ionic formulas are going to be neutrally charged. So their net charges, all the positive charges and all the negative charges are going to net out to be 0. So that's going to be an important thing. So we'll put a star next to this. If your charges don't balance out to be 0, then you don't have the right ionic formula. So it's a good double check on that. And then the second thing we're going to do is, well, I guess this one right here, positive ion. The metal is going to be the first name of this particular compound. So when we're talking about binary ionic compounds, we're talking about compounds made of 2 ions, one positive ion, one negative ion, binary. It's like binary means 2. So when we write the compound, the positive ion, the metal is going to be written first. And it's always going to be written in the simplest whole number ratio when we're writing the formulas. All right, so let me go back up here, grab a snippet of something. So when we're thinking of ionic compounds, I'll bring this down. All right, so when we're thinking of what an ionic compound is, you should think of ionic compounds in this way. Ionic compounds are going to be, like this would be sodium chloride. So its formula would be NaCl. That's actually the first example. When we talk about ionic formula, we're talking about ions that arrange themselves in alternating patterns. So every positive ion has a negative ion next to it, and every negative ion has a positive ion. And they build these like lattice structures, or crystals. This turns out to be a solid crystal. And what ends up happening is this mass of sodium ions and chloride ions, they combine because of their differing charges, like the +1 charge and the -1 charge. They're going to combine so that they actually neutralize. So this whole thing, this whole crystal, is going to have a 0 net charge. Now, in sodium chloride, if we only had like 58 grams of sodium chloride, we would be talking about having 1 mole of sodium chloride. And having 1 mole sodium chloride, let me give myself a little room to work here. So having 1 gram of sodium chloride or 58 grams of sodium chloride. Let me get this to squared again. So 58 grams of sodium chloride, 1 mole sodium chloride, means you have 6.022 times 10 to the 23rd. That's 23rd. Looks like 33rd. Sodium ions and the same number of chloride ions in this particular matrix. So that's a lot. That's like a 10 to the 24th would be like a trillion. So this is quite a large number. So instead of representing what the formula actually represents is like the simplest whole number ratio, this right here. So the simplest whole number ratio between sodium ions and chloride ions is 1 to 1. We have 1 sodium plus 1 ion. We have 1 chloride minus 1 ion. So they're going to combine together to form an ionic compound where sodium ions and chloride ions are going to combine in a 1 to 1 ratio in this large, huge aggregate mass of ions to form a compound which is going to be known as sodium chloride. So sodium chloride's formula is NaCl. All right, so when we actually write the formulas for this, let me get rid of some of this. When we write chemical formulas, it's actually pretty easy to do. You should know that the first name of an ionic formula is the positive ion, and the second name is the negative ion. So we can use the periodic table to come up with what the symbol would be for the calcium ion. So let me grab a periodic table here for a minute. All right, there's one right there. We'll use this instead. There we go. All right, so when we actually have the calcium, here's calcium right here, it's in group number 2. The symbol for the calcium ion would be calcium plus 2. We can predict that because it's in the main group. Remember, the main group is the S and P block. The S block and the P block, these are going to be the main group elements. And all we have to do to predict the charge on the ion is to predict what the atom would have to do to actually gain or lose electrons to become like its nearest noble gas. So calcium would lose 2 electrons to become like argon. So it would have calcium, would have 18 electrons, still around 20 protons. So this overall net charge would be positive 2. Bromine, we can do the same thing. We can take a look at the bromine on here. Bromine's like right there. So the bromine atom would pick up 1 more electron and become Br minus 1. And then what you end up with is a positive 2 charged ion, the cation's plus 2, the anion's negative 1. And if you notice, it doesn't balance out to be 0, so we have to kind of mathematically determine or calculate what it would be. So whatever we need to do to plus 2 charge on this one, we're going to have 2 negative 1 charges to balance it out. And the formula would be written like this, CaBr2. Now, when we're talking about main group elements, so all these elements that we had here, like the sodium, the chlorine, the bromine, and the calcium, they're all in the S and P block, so we can use the periodic table. They only form ions with 1 charge, and we can use the periodic table to figure out what the charges would be. But iron, let me use this one here. Iron's in the D block. It's in the, this is called a transition metal. So elements in the transition metals, right here, this is a transition group. You can't do that because there's an offset on the D block. So after, like on the 19th and 20th electron of the 26 iron has, 19 and 20 go into the 4s, but the rest of them go back and go backwards and backfill to 3d. So there's like a transition, so you can't go back and do the same thing like you do in the main group, the S and P block, representative elements, all those things mean the same thing. So what we do instead is there's no way to predict. Iron could be iron plus 2 or it could be iron plus 3. So it makes it more difficult. There's no real easy way to predict what the charge on the ion would be. So what they do instead is they add on to the cation's name by adding this Roman numeral. So the cation for this one is actually named iron 3. And the symbol for this, that 3 means that the iron has a plus 3 charge. Oxide right here is in a main group, and we can predict its charge based on where it is on the periodic table. It would have a -2 charge. Now, there's another thing you can do on with this, and we'll put it off to the side. This is called the crisscross. Now, some of you I went through this with before Friday. Some of you I did not. So if you already went through this, this is a review. If you haven't seen this before, this is what we covered on the block days. Okay, so on the crisscross method, this is actually easier because you don't actually have to do a lot of math when you do this. So in the crisscross method, what we would do is we would take the charge of the positive ion and use that as a subscript for the oxygen -2. So this would mean that we had 3 oxygen -2 charges, and we would crisscross it the other way too. So the -2 charge on the oxygen means we would have 2 iron plus 3. So if you actually work this out, you can see that mathematically it works out. 2 times +3 is +6, 3 times -2 is -6, and they add up to be a neutral charge 0. The crisscross method always works. I mean, you could have done it with sodium chloride, calcium bromide. You probably don't need to, but the crisscross method is something that will always work, and it's a quick way to come up with a reliable formula. So this would be Fe2O3. All right, pause the tape here and do these last 3 and see what you come up with. Okay, I'm back now. So if you should have a chance to actually have completed the next part. So let's just see what you should have come up with. So magnesium is a main group element. Magnesium's right there. So magnesium, based on where it is on the periodic table, I can predict that it would have a +2 charge. Oxygen, we just had oxygen. It forms the oxide ion, -2 charge. Now I can see here that the charges already balance out. We need 1 magnesium +2 to balance the charge of 1 oxide -2. So these two things will add up to be net out to be 0. We'll have a stable compound. The formula would be MgO. You could have done it by crisscross. You would have taken 1 additional step. You would have ended up with Mg2O2. And just remember, these ratios, we're looking for the simplest whole number ratio. So this number, this Mg2O2, would be simplified down to its nearest, just like you would reduce a fraction. 2/4 could be reduced down to 1/2. We would reduce this one as well. So Mg2O2 would just be MgO, 1-to-1 ratio. Potassium sulfide, these are both main group elements. Potassium's like right there. Sulfide is right there. So the formula for potassium ion would be potassium +1. Formula for the sulfide ion would be sulfur -2. So you can see it's going to take 2 potassium +1s to balance out the sulfide -2. We'll end up with K2S as the formula for that. All right, one word about this one, lead 4. Lead is right here. It's in the main group. But there's something else about lead that we should be aware of. Let me get a little heavier line here. So when we're dealing with lead, whoops, too heavy. When we're dealing with the main group, we should keep in the P block actually is unusual because it has the stair-step line that separates metals from non-metals into 2 different halves. Well, it turns out the metal half, okay, this particular section right in here, this little, I like to think of it like a Bermuda Triangle, sort of. This triangular area right here has elements that they're P block elements. They're technically main group elements, but they're going to behave like the transition elements. As a matter of fact, they have a name. They're called the post-transition elements. So when we have even though they're not technically in the D block, they behave as if they do. And for example, lead could be lead +2 or it could be lead +4. Both of those are possible ions for this particular compound. All right, so when we do this, lead 4, Pb +4, this number, this Roman numeral, is telling